better record it for all the people who are not here. Okay, recording, good. Okay. So, like I said, I have just 2 blank copies, one of test 1 and one of test 2, in case anyone wants them. I'm just trying to share the paper wealth, yeah. And I'm sorry, but I haven't started even marking your tests yet. I'll do them before Monday, though. Don't worry. So today, we're going to start chapter 6, which is on annuities. So annuities are things like mortgages and car payments. So whenever we have these regular payments coming in or going out, right, then we have annuities. Okay? So in section 6.1, we're just going to introduce some ways that we can manipulate the interest rates to be what we need them to be. Okay? And then in 6.2, we'll start introducing the formulas, okay, that we need for the actual calculations. So we're starting chapter 6 on annuities. Oh, I also took a picture of the times for the Learning Center where there's the business math tutor that you can just go and get help for free. If you don't want to come to me, you're always welcome to come to me. But if you want a picture of that, you can send me a text and I'll text the picture to you. How about? I don't know. So chapter 6 is on annuities. Kind of messed up my spelling there. And section 6.1, and like I said, we're just doing 6.1, 6.2 today, in case you've got like a progress bar in your mind going on. So 6.1 is on effective and equivalent interest rates. And equivalent interest rates. I'm going to tell you this right now. Effective rates are really only going to happen in short answer problems on test 3 and on the final, right? Those are the only times that they'll come up, right? So we'll talk about them, I'll introduce them, but do you need to worry about them? No, not really, right? So we'll start with the effective rates. So the effective rate is denoted by I, so the periodic interest rate, and then subscript EFF, so the effective periodic interest rate. Okay. By definition, the effective rate, and we've already calculated effective rates, we just haven't called them that. And so the effective rate is the annually compounded rate that's going to be the same, so yield the same future value as some other compounding frequency. Okay. And so it's the annually compounded rate that will produce the same future value as a given nominal rate R at some compounding frequency F. At some compounding frequency F. We're venturing to the back page of your formula sheet today. And the first formula on there is that the effective rate is 1 plus I to the power of F minus 1. This is on your formula sheet. And what I'm going to do is this formula finds the effective rate, right, from some compounding frequency f. So finds the effective rate from some compounding frequency f. So wait, yeah.
Is that 1 plus I?
Yeah. 1 plus I. So it's 1 plus I to the power of f minus 1. As an example, let's do example 193. Oh, got a buckle here. So what you'll notice is that the effective rate is going from some compounding frequency f to just a frequency of 1, right? Annually compounded. Okay. Later on, we'll develop a more general formula where we can move from some compounding frequency f1 to some other compounding frequency f2, and that's the one that we'll use in all our problems. Okay, but the effective rate is just a special case. Okay. So we want to know what's the effective interest rate of an investment which earns 4.8% compounded quarterly. So here we've got R is 0.048 and F is quarterly, so 4. We can calculate I is R over F, which is 0.048 over 4, which I have here is 0.012. Can only assume that that's true. Check it. 0.048 divided by 4. Sure is. And we want to know what's the effective interest rate. So the effective interest rate is 1 plus I to the power of F minus 1. Which means we have 1 plus 0.012 to the power of F, which is 4, and then minus 1. So we get, I'll do these kind of step by step here to show my work. 1.012 to the power of 4 minus 1. I get 1.048870933 minus 1, which is just 0.048870933. So the effective rate of, what was it? 4.8% compounded quarterly. What it's telling us is that 4.8 compounded quarterly is the same as 4.887% compounded annually. So therefore, what I'm going to do here is I'm going to say this is the same as 4.89%, just rounding a little bit. So therefore, a rate of 4.8% compounded quarterly, oh, you know what, will yield the same future value as 4.89% compounded annually. I'll also say that therefore these rates are equivalent. Right? Therefore, these rates are equivalent. So a special case, we've seen continuously compounded rates, right? And so if we have to go from a continuously compounded rate to an annual rate, we've done that as a problem, right? We saw, okay, so we have 2.5% compounded continuously. What would it have to be compounded annually? So we've done that calculation already, but there's actually a formula that we can use. And so if we have a continuously compounded rate, the effective rate is e to the power of r minus 1. And this is on your formula sheet. Notice that whenever you have e's and logs, it's usually continuous, right? It's because we're dealing with this continuous compounding. We don't really, this would be like a short answer question, right? It's not going to come up in any of the long answer problems that we're working with. Okay. But it's just kind of good to know. And it's on your formula sheet, so we're covering it. Do an example, example 197. An investment earns 6% compounded or continuously compounded interest. What is the effective rate of interest? And so we've got R is 0.06, and the effective rate is e to the power of r minus 1. So we've just got e to the power of 0.06 minus 1. How do you take, so to take e to the power of something on your calculator, you have to have the power, so 0.06 on the screen, and then the second ln button, which has the e to the x above. And so you're going to get, or just make sure that you get 1.061836547 minus 1, which is just 0.061836547. What this is saying is that 6% continuously compounded is the same as 6.18% compounded annually. So here, rounding this to 6.18%, we can say that therefore 6% compounded continuously is equivalent to 6.1% compounded annually. Because that's what the effective rate is. Any questions about that one so far? No? So those two really just kind of short answer problems potentially. But worth knowing, they're on your formula sheet, so may as well know what they are. Let's talk about equivalent interest rates. So equivalent interest rates, that's what we've been doing here. But what we've been doing is the special case where we go from some frequency to a frequency of 1, right? So we've just moved to a frequency of 1. Now we want to be able to move from some frequency F1 to some other frequency F2. Okay? And just to give you some background on why we would want to do that is because we said annuities is when we have these regular payments coming out or going in, right? And so we can't change the payment frequency, but our calculations require us to have the same compounding frequency and the same payment frequency. So what we're going to do, because we can't change when the payments are going in and out, right? We can shift our compounding frequency to match the payment frequency, right? And so that's why we're doing this. Okay? But I'll talk about that again, of course, but just so you know why we're doing this. Okay? So equivalent interest rates are when we have two interest rates. By definition, they have the same effective rate, right? But we know equivalent means they have to be the same, right? They have to be equivalent. And so, yeah, saying that if we found their effective rates, they have to be the same, then yeah, that makes sense. Okay? So by definition, it's two interest rates that have the same effective rate, How we calculate it, we're going to find that I2 is 1 plus I1 to the power of F1, F subscript 1 over F2 minus 1. We're going to talk about all these components here, but this one is going to be really important. This one you're going to use for all your long answer problems for all of chapter 6 and 7 and 8. So it's going to be really important. I'm going to put a double box around it because it's really important. Okay. So what we're doing here is we're moving from some frequency F1 to some new frequency F2, right? So we use this to move from a compounding frequency F1, to a new compounding frequency, F2, right? Where I1 is the old periodic interest rate, old periodic interest rate, and I2 is the new periodic interest rate, right, at the new compounding frequency. So this is the new periodic interest rate. Okay. I'll just show you quickly how we got this formula, right? Where did it come from? You don't have to know it. It's just, I'm going to show you a little bit of math and where it came from. And if you like that kind of stuff, then great. If not, it'll be over soon. So, derived by, we said that the effective rate of the first is equal to the effective rate of the second. So we can start there and say, okay, well, the effective rate of one has to be equal to the effective rate of the other. Okay. We can apply the formulas for the effective rates and say that 1 plus I1 to the power of F1 minus 1, that's the effective rate for the first frequency, is the same as 1 plus I2 to the power of F2 minus 1. We want to solve for I2 because that's our new periodic interest rate. And so here I'm going to say solve for I2. So if we start to move these things over, then we're going to add 1 to one side. So these ones are going to cancel. And so we just get 1 plus I1 to the power of F1 is 1 plus I2 to the power of F2. If I'm trying to solve for I2, I'm trying to get I2 on its own, which means I have to take the F2th root of both sides. Okay. Remember, the shortcut for taking the root is 1 over that value, right? So what we're going to do is we're going to take 1 plus I1 to the power of F1 over F2. That's the same as taking the F2th root of 1 plus I1 to the power of F1, which is 1 plus I2. To get I2 on its own, we subtract 1 from both sides and we get 1 plus I1 to the power of F1 over F2 minus 1 is I2. Like I said, it's neat because you know all this math and you can do all this, right? So that's cool. But do you have to know how to do that? No, absolutely not. Just kind of might be fun to know where it came from. Let's do an example. We'll do example 198. An investment earns 5% interest per year, compounded semi-annually. How much interest should alternative investments, which are compounded quarterly, pay? So now we've got this 5% is our R. It's our R1. Right? because that's where we're starting. And then we're going to move to some new rates, R2. Compounded semi-annually, that's going to be F1 is 2. And we're moving to a compounding frequency of quarterly, which means F2 must be 4. So what we're going to do is, okay, we're going to calculate I1. I1 is R1 over F1, which is 0.05 over 2, so 0.025. That's your first periodic interest rate. And then we're going to calculate I2. I2 is 1 plus I1 to the power of F1 over F2 minus 1. So what we're going to have is we're going to have 1 plus 0.025 to the power of F1. So we were compounding semi-annually. So F1 is 2 divided by, and we're moving to compounding quarterly. So F2 is 4. And then minus 1. So do inside your brackets, then do your power, and then minus 1. So 1.025 to the power of, and I'm going to put my 2 over 4 in brackets. You can simplify it, but it's not always going to be this easy of a fraction to deal with, right? So I'm just going to start putting the powers in the in brackets. So to the power of 2 divided by 4 end bracket equals, and I get 1.0124222837 minus 1. So my periodic interest rate compounding quarterly now is 0.0124222837. If we wanted to. And so in problems that we'll be solving, we're just going to use I2, right? Because we've been using I in our formulas, right? For compound interest, we have to convert R to I. Now there's another step where we have to convert R to I, but then also convert it to I2 to match the payment frequency. Okay? So we just keep adding extra steps basically with every chapter. But once you've got I2, then that's the end. And then that's the interest rate that you use. So what are we saying here? This is, should we answer for R, R1, R2? So I2 is R2 over F2. I2 is 0.0124222837, which is R2 over 4. So this times 4 is, so R2 must be 0.049691346. So in terms of the question, right, 5% compounded semi-annually is equivalent to 4.97% compounded quarterly. So we'll say this is roughly 4.97%. So therefore, 5% compounded semi-annually is equivalent to 4.97% compounded quarterly. We can do the same thing. We've got a special case with continuously compounded interest rates. And so if you have a continuously compounded rate and you want to move to some compounding frequency, right, then we can use this formula. So for continuously compounded interest, we can convert to a different compounding frequency f by I2 is e to the power of r divided by f2 minus 1. This is also on your formula sheet. Again, now we're back to kind of short answer stuff, right? The big I2 that we just talked about, that's going to be the one that you need to hang on to from this section. All these other ones, they're on your formula sheet and we're going to talk about them, but they're really just short answer problems. You know? And so here, I'll just say where F2 is the desired compounding frequency, and in case it's not clear, compounding frequency of I2. Or what if we want to go from some compounding frequency to a continuously compounded rate? We can move that way as well. So, or we can convert, a given rate at some frequency f to a continuously compounded rate by, I'll just use the one on your formula sheet. The textbook just uses, here I'll do, R is F1 times the log of 1 plus I1. The textbook just has, well, it's dropped the subscript ones, but I actually prefer to have them on there, right? Because it just shows you that you're moving from some frequency to a continuous rate, R. This is on your formula sheet. Let's do example 202. Oops. 202. An investment earns 5% interest per year compounded quarterly. What is the equivalent continuously compounded rate? So now you're going from some R1 is 0.05 and F1 is 4. And you want to move to some continuously compounded rate. So we can use the formula R is F1 times the log of 1 plus I1, just from before. Here, oh, I guess I forgot to calculate I1. I'll just do it over here on the side. I1 is R1 over F1, which is 0.05 over 4. I ran out of room. 0.05 over 4, 0.0125. So what I have, I'm moving from a frequency of 4 times the log of 1 plus I1. My periodic interest rate right now is 0.0125. So I have 4 times the log of 1.0125. So plus 1. And then to take the log of this, you just have whatever you need to take the log of on the screen and then hit the LN button. And yeah, I'll just write it out, is 4 times, just so you can check your work, 0.01242252. Then times 4, I get 0.04969,008. Which is roughly 4.97%. So what are we saying then? Therefore, 5% compounded quarterly is equivalent to 4.97% compounded continuously. So therefore, 5% compounded quarterly is equivalent to 4.97% compounded continuously. Let's do example 203. Oops. What monthly compounded rate is equivalent to 9.5% compounded continuously? Right, so now we're starting at a continuous rate and we're moving to a monthly compounded rate. Okay. So here we've got R and we're compounding continuously and moving to an F2 of monthly, which is 12. So from our formula sheet, we have I2, right? If we're moving out of continuous compounds, we have to find I2. So I2 is e to the power of R over F2 minus 1. which we have e to the power of 0.095 divided by f2, which is 12, and then minus 1. So we find 0.095 divided by 12 first. E to the power of 0.0079166 repeating, minus 1. E to the power of that, so you just have it on your screen, and then second ln, we get 1.007948086 minus 1, which of course is just 0.007948086. Notice though that this is I, right? This is your periodic interest rate. So this is only how much interest you're getting each month, right? Because we made it compounding monthly. And so we still have to find R. So I2 is R2 over F2. Oops. I2 is this 0.007948086, which is R2 over 12. So multiply this by 12, and we get R2 is 0.095377036, which roughly is 9.54%, let's say. So therefore, what did we say? 9.5% compounded continuously. 9.5% compounded continuously is equivalent to 9.54% compounded monthly. Good. Questions? All right. So I just want to show you on the formula sheet, right, the ones that we just did. I'll just grab these here. Okay. This one is the really important one, I2. Okay. Here, I'll just say, I'll use a darker green there. These two, the effective rates, the effective rate is moving to F2 equal to 1 always. So they're not really that useful, right? You can just say that in this I2 formula, the one in pink that I've highlighted, right? Then you can just make your F2 equal to 1, and it would be, you would have the same formulas, right? And so those effective ones aren't really that useful, right? Because it's just a special case, right? But let's see if I can find some other colors and do this one. I2 equals e to the r over f2 minus 1. That's when we're moving from some continuous, so f1 is continuous, and f2 is the new rate, or new frequency, sorry. what other color can I use here? Blue. Whereas R equal to F1 times the log of 1 plus I1 is moving from F1 equal to old frequency to some F2, which is continuous. Right. So it's just those special cases. But as you probably noticed, right, continuous and continuously compounded frequencies are pretty rare, right? They'll never come up in a long answer question. And so the effective rates you don't even really need on there. These two are just from the continuously compounded, either moving to continuously compounded or from continuously compounded, which are really rare, right? They don't really happen. So really the only one that you need from all these formulas is that I2 is 1 plus I1 to the power of F1 over F2 minus 1. I only point that out because it's a lot of formulas, but you don't get a lot out of it. Yeah. Any questions about that before we do 6.2? I know you guys are counting them down. And we've still got a little bit of daylight. I can see it. So 6.2, we're just going to introduce annuities. Okay? And then for all of chapter 6 and all of chapter 7, that's what we're going to be doing. We're going to be doing annuities, annuities, annuities. And then in chapter 8, which is our last chapter, we only spend one day on this one section in chapter 8, which is mortgages, which is just a special case of annuities. Okay? So this is all we're going to be doing in one way or another for the rest of the term. So, like I said, an annuity is a series of equal payments at regular intervals. And that's really important, right? They have to be, your monthly car payments or your biweekly loan payments or mortgage payments, right? They come out at regular intervals. Right? So an annuity is a series of equal payments at regular intervals. So just some definitions to get us started. Most of these are pretty straightforward, but the payment interval is the amount of time between payments. The amount of time between payments. Oops. Between payments. The periodic payment is the amount of each payment. Right? So each of the payment amounts. So the periodic payment is the amount of the equal payments in the annuity. Of the equal payments in the annuity. It's denoted by PMT. We've seen that on our calculator, right? We just had it at 0 when we were using it before, but now definitely for chapter 6, 7, and 8, we want to use our calculator, right? Because it's going to make things a lot easier. And so we've got this PMT button that we'll be using quite a bit. Okay? And let's just say that the term is just the duration of the payments, right? How long are you making these payments for, right? Say you get you buy a car and you're making payments for 4 years, that's your term. And then you're done. So the duration of the payments. Here's a note. One mega thing that's going to change is that now, right, n used to be the number of compoundings, the length of the arrow, right? Now, because we've got these regular payments, n is actually going to be the number of payments for annuities. Okay, so that's going to be a kind of a shift that we have to make. Okay. I'll explain why, maybe in a little bit, right? But it's because we have to change our compounding frequency to match the number of payments. So really, n is still the number of compoundings. We're just making sure that they're matching the number of payments, right? So in our minds, it's going to be easier to think about n as the number of payments. So when discussing annuities, n will denote the number of payments I'll put in brackets instead of the number of compoundings. I'm going to highlight this because it's going to be really important. Just to keep in mind. There's going to be 4 types of annuities. The first difference is going to be, okay, are the payments being made at the beginning of the payment period or at the end of the payment period? So we're going to differentiate between when the payments are being made, right? Are you making payments at the beginning of the month or at the end of the month? How we calculate the future value and the present value is going to change a little bit depending on when we make the payments, right? So we have to check that. We'll start by talking about payments at the end of the payment period. The next thing we're going to ask is, does the payment frequency match the compounding frequency? If it does, then we say that we have a simple annuity. I have to check because there's so many names. If it doesn't, which is more likely, then the compounding frequency doesn't have to match the payment frequency, but we are going to calculate I2 to make it match, right? Then we have this general annuity. Okay. And so there are 4 types of annuities. First type is an ordinary annuity. Which is when the payments are at the end of the payment period. So in chapter 6, we're dealing with ordinary annuities. And then in chapter 7, we're going to talk about annuities due. An annuity due is when payments are at the end, or at the beginning, sorry, at the beginning of the payment period. I'll just highlight here. Here's at the end, here's at the beginning. I'll put a little note here that this is from chapter 6, and this is in chapter 7. And then we can further group those, right? An annuity due can be either a simple annuity or a general annuity, or just an ordinary annuity can be a simple annuity or a general annuity. So a simple annuity is when the payment frequency is the same as the compounding frequency. Whereas a general annuity is when the payment frequency is not the same as the compounding frequency. When the payment frequency is not the same as the compounding frequency. What we're going to do here is you would first calculate I2 is 1 plus I1 to the power of F1 over F2 minus 1. And then it just turns into a simple annuity again, right? Because now you've forced the compounding frequency to be the same as the payment frequency. Right? So it's just that extra little step, but not too big of a deal. So an annuity is either ordinary or an annuity due, and also it can be either simple or a general annuity. We ask 2 questions. Right. If we're reading an annuity question, we have to ask these 2 questions, and that'll help us figure out what type of question we have here. When are payments made? If the answer is at the beginning of the payment period, we have an annuity due. If it's at the end of the payment period, we have an ordinary annuity. On your formula sheet, how it's laid out is on the left-hand side, you have ordinary annuities. And then notice on the right-hand side, there's little subscript dues everywhere. So on the right-hand side, you have your annuities due formulas. They're pretty similar, right? If you kind of compare and contrast across, right? So nothing's changing drastically. It's just taking into account that you paid a month earlier, essentially. And the second question we ask is, does the payment frequency match the compounding frequency? Match the compounding frequency. If yes, then you have a simple annuity. If no, you have a general annuity. And need to find I2 first. And need to find I2 first. But then you're back into the same as a simple annuity. Let's talk about ordinary simple annuities. In the case of N payments, we find the future value of ordinary simple annuities using the future value formula on your formula sheet on the left-hand side. We find the future value of ordinary simple annuities by the future value is your payment amount, so PMT, and then big square brackets. In the numerator, 1 plus I to the power of n minus 1 over I. This is on your formula sheet. Notice what's different here from what we're used to. We're used to having the future value and the present value in the same formulas, but that's not the case anymore. Okay. The idea is either you're making these regular payments and you're starting from nothing, right? And you're building it up to some future value, or usually we got a car and now we're paying it off until we have nothing in the end, right? Nothing owing. Okay. And so they're going to be separate. So that's why you have to figure out, okay, do I need a present value or do I need to find my future value? And then that'll help you decide which formula to use. And so, or we can find PV, so the present value, by the present value is the PMT, similar setup, just discounting PMT times big brackets 1 minus 1 plus I to the power of negative n over I. This is, of course, also on your formula sheet. Like I said, depending on if we want to find or if we need to find the future value or the present value, that's going to determine which formula to use. Right? So depending on if we need to find FV or PV, we will need to pick the appropriate formula, of course. As far as our timeline goes, timelines for annuities, oops, can't write at all. Will still look like this, right? We'll start today, and it's going to go for, let's say, 10 years. What we're going to do, because let's say we make yearly payments, right, or annual payments, because it's only 10 years, we could do all the ticks, but even that's a bit much, right? So what we're going to do is you're going to show these endpoints, right, today and whatever the endpoint is. Show the endpoints and then you're going to show at least two ticks in the beginning. Right. Add two more ticks, add 2 ticks in the beginning, and add at least 1 tick at the end. Add ... in between. So what that's going to look like is you're going to have 1 year. If we're doing yearly payments, 2 years, 9 years, ... If the payments are at the end of each year, then we don't have a payment today. The first payment is actually at the 1 year mark. So what we would do is we would have PMT, PMT, and then the ... is just saying, okay, this just keeps going for the years in between. We don't need to show that. And a PMT here and a PMT here. If we're finding the future value of all these payments, for example, how we denote that all these, because technically we could go ahead and calculate each of these future values, right? We would have 10 future values to add up. Already that's a lot of work, right? And so that's when we're going to use this future value formula instead, right? With our payment amount, we have to find I, but so it's a little bit bigger, but saves us a lot of time, right? Instead of calculating these future values individually, which you totally could do, but why would you want to? Okay. But to denote that we're calculating the future values of all these guys, what we're going to do is we're going to join them. You can do a square bracket if you want I just think it's fun to do a curly bracket. Okay. So just kind of funneling them all together and then drawing the arrow from here to say I'm calculating a future value or a present value if you're going back to today. Right. So it's the same idea. It's just now we've got these lumps of payments either going to a present value or a future value. Let's do an example. Oh, any questions first? No. Example 204. Martha contributes $10,000 each year to her RRSP. Good for Martha. At a rate of interest of 7% per year, how much will she have after 25 years? Right. So every year she's putting in $10,000 and it's going to grow at 7% per year. Okay. So first thing we're going to ask, right? And for all of chapter 6, I think chapter 6, I'm pretty sure annuities due is chapter 7. So for all of chapter 6, they're all at the end of the payment period, right? But I'm just going to start. It's good to get in the habit of just making a note. Payments at the end. And what was the other question we had to ask? Is the payment frequency the same as the compounding frequency? What I'm going to do is I'm going to start implementing a P per Y, right? This is your payments per year. We've seen this notation on your calculator, right? So the payments per year, well, she's only making one payment each year. Right? So it's just one. And it looks like the compounding frequency is per year as well. So the compoundings per year is just one. Which means that our payments per year is the same as our compoundings per year. So we don't have to do any conversions. It's supposed to be a check mark. Check. Okay. So let's draw the timeline, see what we're dealing with here. So what we said was, okay, well, we'll start today. And then she's going to go for 25 years. So here at the end, we're at 25 years. She's making payments each year. So for 1 year, 2 years, and then ... and then the last dot and last tick, and then 24 years. Because I want to see at least 3 in the beginning and at least 2 on the end. There's no reason to give me any more though, I guess. So same as before, we put the payment amount underneath. And so each year we've got 10,000, 10,000, 10,000, and 10,000. We want to know how much this is all going to be worth in 25 years. So we want to find what's the future value after 25 years. Remember N? I'm going to put N on the arrow still, right? But N is time times the frequency, right? But now, because N is the number of payments, right? F is the payments per year. Just to adjust for N being the number of payments, but we can still use the same formula. So T is 25 years, and 1 per year, we have 25 payments. We can calculate I. I is R over F, which was 7% per year, so 0.07 over 1, which is 0.07. Nice and simple. Because we know we have to find a future value, we have to use the future value formula. The future value is the payment amount. So each year, that's the payment amount, the 10,000, times 1 plus I to the power of N minus 1 over I. We've got all these values. We know PMT is 10,000. We know I is 0.07, and we know N is 25. So we can just plug these in and solve for the future value. So we've got 10,000 times 1 plus 0.07 to the power of 25 minus 1 over 0.07. Keeping track of your bed mass, right? We have to go inside the big brackets, but then there's more brackets inside. So we have to deal with those brackets first. And I'm just going to go for it here. 1 plus 0.07 to the power of 25 minus 1, because it's actually not worth it to stop and write all these down. Here, I would say just go to, maybe to the big brackets, I don't know. Did I do minus 1 already? I can't remember. 1.07 to the power of 25 minus 1 divided by 0.07. I'll just check in here. But you don't have to. If you went all the way to multiply by 10,000, that's fine. Times 63.24903,772 times 10,000. She'll have $632,490.3772, which in money is $632,490.38. Okay. How much did it actually cost her? She made 25 payments of 10,000. So she made, you're only missing one example. She made 25 payments of $10,000. Right? So it cost her, well, it cost her 25 years, but also 10,000 times 25, just to confirm, it cost her 250,000 to have $632,490.38 after 25 years. That's quite a big difference. Right. Hard to get a rate of 7%, but the idea is the same, right? So even though we're putting in these amounts, right, they're going to amount to something much larger over time. So let's just do a present value example, and then we'll be done for today. Okay. But I feel like we've already kind of introduced basically what you're going to do for all the rest of chapter 6 and chapter 7. So from here on out, it's kind of like, okay, let's get familiar with this stuff. So let's do example 210. Hank borrowed money from Tank. Hank agreed to make yearly payments of $2,500 for 12 years. If Tank charges interest of 13% compounded annually, what was the amount of the loan? And so first, let's just make a note here that the payments per year is 1, and the compoundings per year is also 1. We've got we can calculate I as R over F as well. 13% is 0.13 over 1, which is just 0.13. If we draw out this timeline, let's just visualize what's going on here. He's saying, okay, so let's say he borrowed the money today, and for 12 years, he's going to pay this off by making annual payments. And so he's going to make a payment at 1 year, at 2 years, and then ... to 11 years. And each year he's going to make a payment of $2,500. 2,500, 2,500, 2,500. Whenever we want to find out what the amount of the loan was, we're calculating a present value, right? Because these payments are paying off some value today. Right? And so here, what we're going to do is we're going to funnel these, and we're going to funnel them back to some present value. Same deal here. I'm going to put N is time times the frequency, where the frequency is the payments per year, which is 1. Time is 12 times 1 is just 12. And so now we know the formula for our present value, right? Because now once we've paid off our loan, the future value has to be 0, right? It doesn't do anything. If you've paid off your loan, you don't owe anything else. So the future value is gone, so we need to find the present value. The present value is PMT times 1 minus 1 plus I to the power of negative N over I and bracket. Your payment amount is 2,500 times 1 minus 1 plus I, which we said was 0.13, to the power of negative N, which is 12, over I, which is 0.13. Again, it's just going to be easier if we just kind of plow through, especially this big bracket, remembering to move from inside the little brackets out, do the power, then do 1 minus that value, then divide by 0.13. So 1.13 to the power of, and then I'm going to put 12, negative 12 in brackets equals, and then we want to do 1 minus that, and then divide that by 0.13. You can check your work. You should get 2,500 times 5.9175 647,017. Assuming I did that right. Oh. Yeah, times 2,500. So the loan, 14,794.11754. So in money, he borrowed $14,794.12. How much did it cost them? He borrowed, right? He borrowed $14,794.12, but made 12 payments of 2,500. So 12 times 2,500, total of 30,000. So it cost them 30,000 to borrow $14,794.12. Yikes. Any questions about those? So like I said, we're just going to keep going with these, right? The only difference between a simple annuity and a general annuity is that if the payment and the compounding frequency aren't the same, we have to find I2, but then we can just treat them as if they're the same again, right? So nothing really changes, okay? But we'll do that next day. No questions? No? All right, then we're done. See you guys, oh, I guess on Monday? Yeah, wow, okay, crazy. I'll post a little Moodle quiz just on these rate calculations that we did today, and maybe a couple of future value, present value ones, but it'll be a short 5-question one again. Cool.